Okay, diving right in today with a paper that really shakes things up. The end of manual decoding towards truly end-to-end language models.
Hmm.
I mean, the core claim is pretty bold, they're saying. Calling current LLMs end-to-end is just, well, wrong.
Yeah, it's a strong claim, but they argue it's because of this huge bottleneck, all that manual fiddly tuning of decoding hyperparameters.
Exactly, the temperature, the top piece stuff we all spend ages tweaking.
Right, it's like the Achilles heel. You have these powerful models, but then a human has to manually set these non-differentiable parameters. It kind of breaks the whole autonomous AI promise.
So what's the fix proposed in this paper?
They built something called AutoDeco.
AutoDeco.
Yeah, it's this new lightweight architecture designed to make generations self-regulating. Basically, it learns to predict the best temperature and top heap settings on the fly. Context-specific for the very next token it's about to generate. And it all happens inside the normal forward pass.
Wow, okay, so dynamic adjustments during generation?
Exactly. Truly end-to-end this time.
And what are the big takeaways? Like, does it work?
Oh, it works. The results are pretty impressive. AutoDeco significantly beats the standard static decoding strategies we usually use. But here's the real kicker. It basically matches or even beats what they call the Oracle-tuned baselines.
Oracle-tuned. You mean like the absolute best you could possibly get if you cheated and knew the perfect static settings beforehand?
Precisely. The practical upper limit for any static approach. AutoDeco gets there automatically in one pass.
So it's already doing better than the theoretical best a human could manually tune for a static setting. That's huge. And the cost? Is it slow?
That's another big win. The latency overhead is tiny, typically just 1 to 2% extra time. Really negligible.
Okay, minimal cost, better than Oracle performance. What else?
Well, maybe the most surprising thing is this emergent capability they found.
Go on.
The model, with AutoDeco, actually started to understand natural language commands about how it should generate text.
Wait, like telling it be more creative?
Yeah, exactly like that. Or be more certain. And it would adjust its internal temperature and top up predictions accordingly, dynamically, token by token.
Okay, that sounds like a genuine paradigm shift. We need to unpack that. Let's start with that core problem, the static decoding bottleneck. We've all been there, right? Wasting hours tweaking those knobs.
Totally. You have these incredible models, billions of parameters, but whether you get genius or garbage often comes down to picking one static temperature value. It feels primitive.
And the paper points out it's not just about finding one good setting because the best setting changes all the time, right?
Absolutely. It's highly task dependent. You look at commercial API docs, they recommend different settings for classification versus, say, brainstorming.
What works for writing code won't work for writing a poem.
Exactly. But the paper argues the problem is even deeper. It's not just task dependent.
Right.
A single static setting is often suboptimal, even within a single answer.
Okay, explain that. How can it be suboptimal within one generation?
Think about solving a complex math problem or any reasoning task. Initially, the model might need to be creative, explore different lines of thought. That needs higher temperature, more randomness.
Right, exploring possibilities.
But then, once it figures out the path and needs to give the final precise answer, you want the opposite. You want low temperature, high certainty, stick to the facts.
Ah, I see. So it needs to switch strategy midstream.
Precisely. And current systems with one static setting, they just can't do that.
Yeah.
It's like trying to listen to music that jumps between loud and quiet with the volume knob fixed in one place. It doesn't work well for either extreme.
Okay, so that sets the stage perfectly for AutoDeco. How does it actually provide that dynamic control?
So it works by augmenting the standard transformer. They add these small, lightweight prediction heads.
Prediction heads, what do they predict?
They look at the current internal state of the hidden state for the current token, and they predict the best temperature, that's called $24, and the best top-up value for generating the next token.
So it's constantly adjusting its own sampling strategy based on its internal context.
Exactly. It creates this self-regulating loop, effectively eliminating that whole manual tuning step.
Conceptually, that makes a ton of sense. But the implementation must have been tricky. How do you train those heads?
Yeah, that's the core technical hurdle they had to overcome.
Because standard sampling, like top-up or nucleus sampling, isn't differentiable, right? It has that hard cutoff.
Exactly. That's the crux of it. Standard top-up calculates the cumulative probability of tokens sorted by likelihood, and once you hit your threshold, say P 0.9, everything else just gets zero probability.
Poof! And that poof, that hard zero, kills the gradient.
Kills it dead. If a token's probability is zero, slightly changing the top-up threshold that caused it to be zero doesn't change the output probability. So no gradient signal flows back. You can't learn.
It's like trying to learn how to use a dimmer switch when you only have an on-off switch.
Perfect analogy. So if you can't backpropagate the error signal from the final output back to the head that predicted the top at value,
Yeah.
you can't train that head to make better predictions.
Okay, so AutoDeco needed a differentiable version of top hit, at least for training.
Precisely. And
Yeah.
that's their key innovation. A novel, differentiable, soft top-et mechanism.
Soft top hit, so no hard cutoff.
Right. Instead of abruptly zeroing out probabilities for tokens outside the predicted nucleus, this soft mechanism applies a smooth, differentiable scaling factor. Tokens far outside the nucleus see their probabilities gently decay towards zero rather than hitting a wall. They use an exponential decay based on how far the cumulative probability is from the threshold cut.
So it creates a smooth slope instead of a cliff edge.
Exactly. And because it's smooth, it's differentiable. This is the breakthrough.
Because now the gradients can flow.
Yes. Gradients from the standard cross-entropy loss, which measures how good the final prediction was, can now flow all the way back, not just to the main model, but also to the head's predicting temperature. And the soft top threshold, it allows the model to learn end-to-end how to set its own sampling parameters.
That's really clever. And how complex was the training itself? Did they need massive resources?
That's another really appealing part. They were quite efficient. They actually froze the parameters of the base LLM.
Froze the whole thing. So no expensive retraining of the giant model?
None at all. They only trained the new lightweight AutoDeco heads. These are tiny, just simple MLPs.
Then training data.
They used reject sampling trajectories from the GMath 103K dataset. And get this, it only took about 400 steps of fine-tuning. Really fast.
Wow, 400 steps. That's incredibly efficient. They also mentioned a couple of tricks to make the training more robust, right? Something about masking?
Yeah, two important debiasing techniques. The first was easy token masking.
Okay, what's that?
Well, think about it. Most tokens an LLM predicts are easy, like the U or a comma. The greedy prediction is usually correct. The optimal temperature for these is basically zero. If you train the prediction head on too many of these easy cases, it learns to be overly conservative, always predicting low temperature and low teppa.
Ah, so it gets biased towards certainty.
Exactly. So they randomly masked the training loss for a large chunk, like 60% of these easy tokens, where the greedy choice was already right. This forced the AutoDeco heads to focus their learning on the more difficult tokens, the ones where the model was actually uncertain and needed dynamic decoding the most.
Makes sense. Focus on the hard cases. What was the second trick?
Dynamic fine-tuning. This is about reweighting the loss. It focused training on tokens where the model had reasonable prior uncertainty. It prevents the head from learning to predict, say, very high temperatures for tokens where the model was already extremely uncertain, like near uniform probability distributions. It teaches the head to use high temperatures more judiciously when it makes sense.
Got it. So, clever training on just the small heads, focusing on the informative examples. Okay, let's talk deployment. This sounds great in theory, but if you're an engineer listening, you're probably wondering about the overhead. Does AutoDeco slow things down?
That's critical, and the answer is, thankfully, no, not really. The overhead is minimal. Remember, the prediction heads are just small, two-layer MLPs. Their computation is done as part of the standard forward pass.
So how minimal are we talking?
It adds only about 1 to 2% to the total generation time, like 0.3 to 0.6 seconds extra per 1,000 tokens generated. It's barely noticeable.
Okay, 1–2% latency increase is definitely acceptable for most applications. What about memory or complexity? Is it hard to integrate?
Also very lean. It adds only about 4 megabytes to the model size, which is tiny. And they designed it as a drop-in replacement. The paper emphasizes it's basically a one-line code change in standard inference libraries to switch from static decoding to using AutoDeco.
A one-line change. Okay, now you're speaking in engineer's language. That makes adoption incredibly easy.
Exactly. Low cost, easy integration.
All right, practicality's covered. Let's get to the juicy part, performance. How well does AutoDeco actually generate text compared to the old ways?
So they tested it thoroughly across 8 different benchmarks, using models from the Llama, Quinn, and GPT families. On the in-domain tasks, remember, it was trained on math. The gains were substantial. For Llama Nematron 8B, AutoDeco improved the average score by almost 3.5 absolute points compared to the default static sampling. That's a big jump.
Okay, strong results on the training domain. But what about generalization? Does it only work for math problems?
This is where it gets really interesting and maybe a bit counterintuitive. Despite being trained only on math, AutoDeco showed strong performance gains on completely different out-of-domain tasks. Things like general question answering, code generation, even instruction following.
Whoa, hold on. Trained on math, but improves general QA and coding. How does that work?
That's one of the key insights, I think. It suggests AutoDeco isn't just learning tricks for math problems. It seems to be learning a more fundamental meta skill.
A meta skill.
Yeah, like the general skill of how to generate text effectively, how to balance exploration, creativity, higher temperature, versus exploitation, precision, lower temperature. Apparently, those core principles apply whether you're reasoning through an equation, writing Python code, or answering a general knowledge question.
So it learned a universal generation strategy from a specific domain.
It seems that way. The generalization was surprisingly strong. Sometimes the gains were even larger out of domain than in domain.
That's fascinating. Okay, and you mentioned earlier it competes with the Oracle baseline.
Right, the expert guided tuning. That baseline is basically finding the single best static temperature and top setting for each specific benchmark after looking at the test set answers. It's cheating, essentially. You can't do that in the real world.
It's the theoretical ceiling for static methods.
Exactly. And AutoDeco, running in a single pass with no prior knowledge in the test set, performs almost identically to this Oracle, often just a fraction of a point behind.
Which means, for any practical purpose where you can't cheat, AutoDeco is effectively giving you the best possible result you could have hoped for from static tuning, but automatically.
Precisely. It removes that impossible burden of finding the perfect static setting for every single different scenario.
And the paper had that great example, right? Llama Nematron needed totally different optimal static settings for math versus QA.
Yeah, like T0.8, P0.9 for one task, and T0.3, P0.6 for another. It's impossible for a developer to know which setting to use for any given user query beforehand. AutoDeco just handles it.
Okay, one more performance point. The pass at K results. Does the benefit hold up if you generate multiple potential answers?
It does. And the relative benefit actually gets bigger. The absolute point gains were consistent as you increase K, the number of generated candidates, up to 64. But because the baseline accuracy naturally gets higher with more attempts, higher K, that same absolute gain represents a much larger percentage reduction in the remaining errors.
Ah, so the error reduction gets amplified.
Exactly. For one of the models, OpenAI GPT-OSS20B, the relative error reduction went from about 3.5% at pass at one attempt to over 18% at pass at 64. The impact grows.
Very cool. Okay, let's switch gears to what might be the most mind-bending part. This emergent natural language control.
Yeah, this was definitely the most surprising finding for the researchers, and I think for many readers too.
So the model wasn't explicitly trained to follow commands like be more creative, right?
Not initially, no.
Yeah.
It was trained to optimize for correctness, primarily on math problems using those reject sampling trajectories. But somehow it learned this connection implicitly.
So what happened when they just tried giving it commands?
It just worked. They'd add a sentence to the prompt like, I hope the answers can be more innovative and diverse. And they observed that the internal end values predicted by AutoDeco would spontaneously increase during the generation that followed. The model turned up its own randomness.
Wow, and the opposite for certainty.
Yep. Prompt it with something like, I hope the answers can be as certain as possible, and the predicted Haddo values would go down. It became more deterministic.
That's incredible. It's like the model learned to map the meaning of diverse or certain directly onto its internal sampling parameters.
It seems to be the first clear demonstration of an LLM translating that kind of abstract user intent into concrete token-level adjustments of its own generation strategy.
Was it reliable at first, or more like a hint of a capability?
It was somewhat inconsistent initially, a promising emergent behavior, but not something you could, say, build an API around immediately.
So how did they make it robust?
They did some targeted fine-tuning specifically for this. They used a ranking loss approach. They gave the model pairs of prompts, one neutral, one with a decoding control command, like be more diverse or be less random, and trained the AutoDeco heads to predict temperatures and top values that shifted in the correct direction compared to the neutral baseline.
So explicitly teaching it the relationship between the command words and the desired parameter shift.
Exactly. And that targeted training worked really well.
How well? Quantitatively.
They showed that the low diversity command, for example, reliably caused the average predicted temperature to drop significantly from around 0.72 down to 0.61. And crucially, it did this with 99% consistency.
99% consistency. Okay, that's something you can build features on. That's reliable control.
Definitely. It proves that this connection is real and exploitable. It opens up new ways for users to interact with and steer LLMs using just natural language.
So let's wrap this up. What's the big picture here?
Well, AutoDeco seems to successfully tackle that long-standing bottleneck of manual decoding. It makes LLM generation dynamic, self-regulating. It achieves, state-of-the-art performance, often matching or beating the theoretical best static settings, shows great generalization, and introduces this amazing natural language control capability.
And all with minimal computational cost and easy integration.
Right. It transforms decoding from this external manual chore into an internal learned skill of the model itself.
What about next steps? Where does the research go from here?
The paper mentions the next frontier is achieving precise, absolute control via language. Right now, it's directional, more diverse, makes T go up. But they want to get to a point where you can say, set temperature to exactly 0.2 and have it obey perfectly.
Fine-grained, absolute control.
Yeah. And they hypothesized that getting that level of precision might require going beyond just training the heads. It might need joint training of the base LLM and the AutoDeco heads together.
Because the frozen backbone might have inherent limitations or biases that prevent perfect control by just the heads alone.
That seems to be the idea. Joint training could allow the entire system to adapt for that precise level of control.
Okay, final thought. You mentioned that fascinating generalization, learning the meta skill of generation from just math data. What does that imply for how we train models in the future?
That's the really provocative question, isn't it? If a model can learn such a universal skill, how to balance creativity and precision from a narrow but high-signal domain like math, using just a lightweight add-on like AutoDeco, well, does that challenge the common wisdom that you need massive, diverse, task-specific data for fine-tuning everything?
You mean maybe we don't need giant data sets for every aspect of control?
Perhaps. Maybe the future involves training core capabilities on focused data and then adding these kinds of modular lightweight control layers like AutoDeco to handle things like decoding strategy or style. It hints at a potentially much more efficient modular approach to building sophisticated AI.
Instead of one monolithic model trained on everything, maybe it's a strong core with specialized, efficiently trained modules plugged in.
It definitely makes you think about where the leverage is in the training process. A really interesting direction to watch.